You good? You good on audio? Everybody hear me? Good? All right. We'll go ahead and get started. I'll do a grand introduction of who I am and stuff like that. So today we're going to be talking about a special little project that I've been working on for the last few months called the Harbinger Sensor Network Project. But we're going to talk about a DIY approach to building wireless sensor networks. We're going to discuss some reasons why you may want to do this, as well as a few other things. So a little, just briefly about who I am. My name's Tim Fowler. I'm an ethical hacker with Parameter Security as of 8 days ago. I just moved to St. Louis a few days before the conference started, so I'm really tired. But I'm really excited to be here. I'm really excited to be in the St. Louis area and with Parameter. A little more details that pretty much defines me. I'm Christian. I've got my OSWP. I put that in there because we're talking about wireless. I'm a big open source advocate. Have spent a lot of time developing open source software, working with Linux and different things like that. I love Wi-Fi. I absolutely love Wi-Fi. I started hacking Wi-Fi. That's how I got started. And because of all of the amazing things that you can do with Wi-Fi, I hate Wi-Fi. I don't trust Wi-Fi. I don't trust anybody else's Wi-Fi. And we're going to look at some of the reasons why you probably shouldn't either and stuff. And lately I decided I was going to try to lose some weight last year and took up triathlon. Fun stuff. I'm down about 152 pounds in 13 months. So this is my biggest accomplishment. I really enjoy doing conferences and speaking and stuff, and so I decided that if I wanted to be around and do it for a very long time, I should probably get a little healthier. So, but anyway, that's me in a nutshell. I'm not super special. I enjoy hanging out and talking to people. But to understand kind of where this entire talk is going and this project is going, we've got to do a lot of background. Because sensor networks, this is not an original concept, that I really have not done anything new. They've been around for a while. There's been a lot of other variations and stuff. And a few years ago, I came across several different projects. The first one was called Creepy Doll. Anybody familiar with that? Introduced by Brendan O'Connor at Black Hat 2011, I believe. It may have been 2012. I'm not sure. Can't remember exactly. Anyway, it was a distributed sensor network. Did a lot of really cool things with it, but I didn't like it because it didn't meet all of my needs. It did some things that I didn't like it, and being the open source guy that I am and stuff, it's like, yeah, eventually we'll just write our own. But it's a really good tool. We did a lot of great work in it, and they got a lot of publicity about it. Ars Technica, of course, we typically see one or two stories coming out of Black Hat DEF CON. They just kind of catch fire and stuff. And this was a Creepy Doll here. He basically has like 10 Raspberry Pis, very cheap hardware, very cheap sensors. He classifies them as disposable sensors. He was very strategic in the way he sources hardware and stuff like that. So if he lost one that was discovered or things like that, it really didn't matter. He actually called the sensors F-bombs, which is something falling obstacles, something ballistic. Basically, he designed these things to chunk them over walls and onto roofs and things like that, and for them to be able to survive. It was really cool project. He released all the code, open source, really good stuff. Like I said, I started playing around with this, and it does some really cool things, but there was a few things that I just didn't like. So I started looking for a different solution. And not too long after that, I found a project that was called Snoopy. It was released by a company out of, I want to say, South Africa, SensePost. And it was another distributed sensor network project. It was very similar to Creepy Doll in some ways, but they took a different approach to it. One of the things that Snoopy does is it is very active, meaning that it actually interacts with devices moving through the network and stuff like that, which is great for specific types of data that you're wanting to collect and stuff like that. The problem is I was wanting to figure out a solution that's completely passive. I don't want to interact with clients and devices and stuff. I kind of treat them like Schrodinger's cat, that it's either dead or alive. Well, in this case, by doing passive, I'm not doing any kind of interaction. I'm not manipulating the data in any way. It's data in its purest form. And so that I'm able to do a lot more, what I can classify as much more accurate processing and analysis of that. And so these projects laid the groundwork. A Black Hat 2013 Asia, since post, they attached one of these sensors to a drone and started flying it all over the place, capturing just bukus and bukus of wireless data. A lot of people were upset, got mad. I thought it was hilarious. Because now all of a sudden we're starting to do data collection from the sky and things like that. So it was really cool. Well, from that came probably one of the most far-fetched presentations I've ever done. Last year I was invited to speak with the EC Council's Hacker Halted in Atlanta, Georgia. And they had a theme of the zombie apocalypse. My primary domain is wireless hacking. And I was trying to figure out how in the world am I going to create a presentation with wireless and zombies. And it took about 45 seconds for me to actually come up with the entire thesis. And it looks something like this: when zombies take to the airwaves. And the little graphics down at the bottom pretty much can tell you the whole story. We all, raise your hand if you have a smartphone or a tablet within reach of you right now. Basically everybody. The premise was, in the zombie apocalypse, you're going to have a bunch of people carrying a bunch of devices, and then they're going to get infected. And now we're going to have zombies carrying smartphones, which is probably just a terrifying concept anyway. But the thing about it, zombies, hopefully, depending on any zombie experts here, because we can argue about zombies and we'll both be wrong. And so I just had this premise that they would basically not have a lot of human function. They wouldn't have a use for a cell phone. They're definitely not going to charge it and stuff like that. But because we have a sensor network in place that we could actually utilize wireless technologies and things like that to kind of monitor in near real time the zombie infestation. We could see when people were becoming infected. We could see the population density in certain areas. But more importantly, that we could actually proactively take to the airwaves and send out communications and stuff to help our population get to safety and things like that. Like I said, it was a really kind of far-fetched concept until you realize that we actually are a complete society of data zombies. We have these devices, we carry them around everywhere, and they are hemorrhaging data. I mean, so much data comes out of our mobile devices that people just don't understand. And it's not just wireless. It's Bluetooth. It's every possible radio frequency that they can pack into this device, and they're going to keep packing them in because we're going to just keep generating more data, and they want more ways to capture it and stuff. And so I started doing some research. And there's a lot of commercial sensor setups for data analytics. A lot of retail companies will buy these things, and they'll track people's movements through their stores, figure out which areas of their stores are trafficked a lot, how long people are staying there. They also have the ability to basically determine whether they were able to convert into a sale by detecting close proximity at cash registers. They could do special offerings and stuff. If you ever, Kohl's, any Kohl's fans? Anybody ever notice if you join their wireless, you get special coupons? Anybody know how that works? They're tracking you. They know how long, when the last time you were there, how frequently you come back, and things like that. And so it was this concept, it was like, how far could I take it from a DIY approach? Typically, these sensor deployments and stuff are very, very expensive because what you're really paying for is the analytics side on the back end. You got, you can have all the data in the world, but if you can't process it and get some kind of tangible result out of it, it's really just not useful. So the analytics is really important in any kind of data set but specifically in a sensor network, we need to have the ability to process and get really, really interesting data out. So I did that presentation a couple of times last year. A lot of people seemed to like it. In fact, one Friday morning in October, my phone was blowing up at like 6:30 in the morning. People all over Twitter is like, hey, you need to wake up, go check this thing out. I get online, and it's the Register in the UK runs this article called Put Down Your Shotguns, and it's actually a article on my presentation, When Zombies Take to the Airwaves, which I thought was really awesome until I realized that was nothing more than clickbait because the season premiere of The Walking Dead was on that Sunday. And they had saved it for like 3 weeks just so that they could get a bunch of clickbait. But hey, it was still cool for me. But I kept getting asked this one question because I was proposing a lot of kind of theoretical scenarios that I knew to be factual. But the question that people kept asking is like, have you done this? Have you built these networks? Have you built these sensors? Have you done this? And the answer was kind of, sort of, yes. I've played with Creepy Doll. I've played with SensePost. I've played with some other stuff. But they never really just were satisfying to me because they would do certain things really well, and then the other things like I really didn't like the active being able to manipulate clients, essentially your social engineering devices, to connect to you and generate traffic and to do other stuff. Like, I really don't care that you're surfing Facebook. I just don't. Like, that data doesn't appeal to me, but for certain projects, that's what they want to know. They want to know what type of device you have, what operating system you're running, and stuff like that. I didn't need that data. I simply was more curious about the presence of devices within in a network. So when I set out each year in December, I start looking at what I'm going to do for the next year in terms of talks and presentations, as well as projects, because I like to try to have a project every year or so that's pretty comprehensive. And I was like, well, what am I going to do? What am I going to do? And it just dawned on me, I was like, well, why don't we do it? Why don't we actually make the sensor network, take the theoretical from last year, the zombie apocalypse, and let's do it. So back in February, I was at B-Sides Huntsville. I was able to release the first iteration of the Harbinger Sensor Network project. And this is what we're talking about today. I can go ahead and tell you that a new version of the sensor code was pushed at about 5:37 a.m. this morning. I'm very, very tired. But we'll get into the code a little bit. I chose Harbinger as the name for this project for a very, very specific reason. The definition of Harbinger is a person or thing that announces or signals the approach of another. I had very, very clear objectives when creating this project because, like I said, there's other sensor network projects. There's entire analytics companies that this is all they do. One example is Euclid Analytics. If you go to Euclid Analytics website and stuff, like verbatim, it's sensor network, data collection, all this stuff. It's like all of this stuff that, not to go like all conspiracy theory and like anti-government and NSA, all the stuff we were really concerned with like the NSA, they're like, yeah, we're doing that, just on a smaller scale. But nobody complains about it because it's a company and not a government. But anyway, so with HSNP or Harbinger, like I said, I had some very, very key objectives. The first was to create a distributed sensor network for data collection and traffic flow migratory pathway analysis. That's a bunch of just fancy words, but basically what it means is I wanted to see how devices move in a closed ecosystem. What I mean by a closed ecosystem, probably a better term is a predefined ecosystem. So how many of you drove to the casino today? Okay. How many of you went off-road to do so? Why not? Because we have a predefined ecosystem. We take roads. We have some social conventions that, we typically obey the speed limits and try to do turn signals and things like that. So we have this predefined ecosystem. But did you know that if you actually look at the traffic over a period of time, that you actually start to see these small, what was called deep sets of data, of these small variations in which people travel in a predefined manner. Meaning, if we're going from point A to point B, all of us, statistically, I'm not sure how many people's in here, I'll say about 150 or so, 9 of us are going to take a completely different route than everybody else. Same ecosystem. Why? Maybe faster, maybe you know something I don't, maybe you know about construction, you know about that one red light that you're going to sit at for 47 minutes. There's a lot of factors that go on in this, and so this is what I was really interested in looking at, is how devices can move through a closed ecosystem or a predefined ecosystem and find the small variations, because the small variations in the migratory patterns of... Let me back up just right quick. When I say devices, please understand device and people, device person is the same. Okay? If you have a device on you and the device has the ability to be tracked, guess what? Know where the device is, I know where you're at. And this is one thing, and I don't know why that just popped up, that's really important to understand. If you're already thinking that I am building a mass surveillance network, you could be right. You could be wrong. A lot of it has to do with the general application. This is part of the reason why I was very specific in my objectives. Because I have an actual goal. What somebody else does with it, that's their business and stuff. But for, let's not beat around the bush. Yeah, this is a way that you can track people. Through an office building, through cities, through whatever grid network you want to set up, you've got the ability to do that. The next big objective for this project is to create the analytics engine and data processing with visualization rendering. Okay. I like shiny stuff. Any C-level executives or anything like that in here? Okay. If you ever have these meetings and stuff, they like flow charts and pie charts and just shiny, beautiful pictures and stuff like that. I want to be able to take the data and do something visually with it, give you a representation of what's happening and stuff like that. Because if we don't have the ability to process and consume the data is useless. So I can collect all the data I want. What good is it doing if I can't actually take the processing and the analytics of it and produce something beneficial, something informative, or whatever? So, why? I get asked this question a lot, and there's just one answer. Because I can. And this is a multifaceted answer. One, because I love wireless and I hate wireless for the same reasons. It's something that I'm very passionate about. I love data. I am a adequate programmer. And if you look at my code, you'll probably disagree with that completely. This was a challenge because there's multi-stages, there's multiple kind of milestones within this project, and they're huge. The analytics side of this thing is really, really daunting, especially when we get to look at just how much data I can possibly be pulling in on a single node. You multiply this by 200, 300 nodes, it is a ton of data, and being able to extrapolate pertinent information out of that. So that was the big challenge. I wanted a challenge. I wanted something that was going to challenge me programmatically, something that was going to challenge me philosophically in terms of how my approach was, and things. But ultimately, it's just kind of fun and gives me something to do. But because all these other projects exist, why should I reinvent the wheel? Because I don't believe in reinventing the wheel. There's no sense in it. But in this case, there were certain elements that I had to go, that just won't work because of X, Y, and Z. And we're going to talk about that. So Harbinger is a wireless sensor project for historical and trend predictive analysis as well. So it talked about the migratory flow patterns and stuff like that. Ultimately, the true objective is to be able to predict where a device will go upon the first time it enters the network. Well, the only way to do that is to capture a ridiculous amount of data, process a lot of that data, and figure out what the small, minute, deep set of movements are, so that within a statistical model, a new device has just entered the network at this location. Survey says they're probably going to the casino. And then I find out whether I'm right or not. And then you'd run the data again. Every single time. You just keep going. It never stops. So eventually it's designed, it's any amateur meteorology fans? That's how we do it. We have a bunch of storms, we collect a bunch of data, and we throw that into a model for the next time. And it's wrong. So we throw more data in it. It gets slightly better. And we keep doing this again. Anybody know how they predict earthquake zones? Where there's been earthquakes, historically. If you pull up a map, a geological map of the earthquake zones, pull up a geological map of earthquakes over time. There's a 1-to-1 correlation. But how did we come up with these hot zones and stuff? We had to look at the data. We had to analyze data going, hey, this is happening a lot right here. Obviously, we found the faults and stuff. Same thing. What is bird watching and stuff? I forgot what that's called. Anyway, migratory birds. Migratory, like whales and stuff like that. How do we know where they go, when they come back? We've watched it. We've collected the data. We've seen it. We've been able to create these predictive models. How do we know that a species of birds is on the verge of extinction? One of the big keys is there's a change in the migration patterns. Could be environmental, could be something potentially genetic or something like that. But we have to process this. We're doing this kind of analyzation in so many different realms. I just wanted to do it on people. There's no way else to say it. Unlike other sensor projects, Harbinger is completely passive on the airwaves. I do not interact with any device at any point in time that's going through the network. It's my belief that this keeps it, it's a twofold. One, I'm not manipulating the data. Okay? I'm not generating traffic or anything like that. Everything's just happening as normal. There's not all of a sudden new wireless networks for people to connect their devices to and stuff. Normal behavior. I feel like that's the best approach. The other thing, and this will go to your conspiracy theorists, it's virtually undetectable. It's passive. It's just listening. It's literally like walking into a room and not saying a word and just listening to all the conversations that are going on. There could be a potential Fourth Amendment issue, especially if you're in law enforcement, government agencies. It could be an invasion of privacy. As a private citizen, you get a little more leeway with certain stuff like that. So, if somebody is not going to be happy that I'm setting up a sensor network and stuff and capturing all this data, it's probably best to do it in a way that minimizes my chance of actually getting called. Not that I'm really afraid of it, but some people may be. And so this is why I wanted to make sure that it's as passive as possible. There is the ability to do transmission, but that's only for data acquisition. It's still not interacting with clients and stuff. But very, very, very important and dear to my heart, Harbinger is an open source project, and it is licensed under the GPL v3. Quick side note, because I am an open source advocate, just because you publish your code on GitHub does not mean it's open source. You have to apply a license to it. Otherwise, it's all rights reserved. Most people don't know that. How I know that, that's a long story. Anyway, so the requirements, it must be open source. We've pretty much taken care of that. Must be hardware agnostic as possible to keep the cost down and allow people to use basically whatever hardware they choose. If you were at Huntsville, and I don't recognize anybody that's in Huntsville, I failed miserably at this. I had a ideal platform that I wanted to use. I built the code. It was working on all my test machines, of course. And then I went to go to my hardware platform, and there was a chipset issue, and I was getting nothing but trash in my captures. Really, really frustrating. But this is what happens when you write code and stuff, especially when you're having to deal with cross-platforms and stuff like that. Luckily, I fixed most of those issues with the new code. I also wanted to keep the dependencies and the requirements to a minimum. Some of these projects, you'll go and download 300 lines of code and 200 dependencies. It's probably not a very good project if you're having to put that much stuff together. So I want to keep it really low in terms of the dependencies. Actually, we'll get into what's required for that. And it must scale. This needs to go from 1 sensor to 10,000. I just thought 10,000 sensors would be really fun. If anybody wants to help sponsor that, let me know. Because even on the cheapest platform, I mean, if you can do $25 with Raspberry Pi A, some batteries, a wireless adapter stuff, you're looking really about $45. So, anybody got $500,000 and we'll set one of these things up. I'll even name it after you. But I need it to scale. And the reason why I need it to scale is because of the sheer volume of data that we're going to be collecting and things like that. So, there's 3 primary elements to Harbinger. There's really now 4, and I'll talk about that just briefly. But the first and key, you got to be able to collect the data. How are you going to collect the data? You got to have the sensor. So, what we've got right now is the actual sensor node software for being able to do the baseline data collection and monitoring. The next stage is the actual centralized data management, and then the final will be the analytics and data visualization to wrap everything up in a comprehensive package. So, stage 1, it's the sensor nodes. If you go and look at the code after we're done here and stuff, what you'll realize is that's all that's there right now, and that's by design. Only stage 1 sensor node code is available because that's where everything starts. I want people kind of playing around with it, getting an idea of what it's going to be able to do. The node requirements are very, very simple, except there is one thing that's missing on here. You got to be able to run Python, 2.7 preferred. SQLite, which this is actually going to be replaced in the final production release, probably in November. A wireless interface that supports monitor mode. And the one addition in the code rewrite is I had to go to using Scapy to do a lot of the data collection. It's really not that major of a dependency. But it works. I've got a lot of cross compilers and stuff like that. Scapy's basically on any platform that Python runs on and stuff. So very minimum from a software standpoint. There will be one addition with the SQLite that's going array. We'll get into the data collection in a moment. Hardware suggestions, whatever you got, ultimately. Raspberry Pi, A, B, B+2, BeagleBones, TP-Link MR3040, and I've got an asterisk by that because that is my favorite platform right now. Wireless adapters, anything that supports monitor mode. You don't even have to support injection, which opens it up to even a wider variety of interface and stuff. Most laptop cards today, like even the Intels, will do monitor mode. They may not do packet injection for like wireless attacks, but you can actually get them to listen to the airways of stuff. The TP-Link down at the bottom, the WN722N, you can get these things for like $13 on Amazon. Really, really good cards. If you can spend the money, I always would recommend an Alpha and stuff. But basically, whatever you got. Okay, the code as it stands right now works on Atheros, most raw links, and a few Broadcoms that actually support monitor mode. Intel, basically the full gambit. If you can use it with AirCrack in G Suite, we can use it. So hardware, choose what you want. You can make these sensors as big or as small as you can do it. A lot of it's going to depend on how large of a network you're going to actually make. So there's a few requirements in terms of what data we need to collect. And they're very small. Very, very small. We need every single probe request that comes through the sensor or through the network. We need the date in which the client appeared in the network, when it last appeared. We need timestamps on everything, basically. We need to be able to determine the last seen in the network. And this is from the client side, and then from the access point side, we need to see probe response and the time in which it takes to respond. And basically have a blank slide here for some reason. Don't know why. So just visualize the data schema as presented here. No, and the data schema, we'll actually look at the data schema once we jump into the SQLite database here. It's not a lot, but what those 5 things: probe request, probe response, and all the timestamps, first seen, last seen, stuff like that. That is some ridiculously powerful information. It seems very innocent. When you start collecting this stuff over weeks, days, months, over a wide area, it is unnerving how much information you can actually determine about an individual device from habits and stuff like that. Like, John Smith likes to go to Starbucks at 2:37 in the afternoon on Fridays. You can get that granular with the data. So where to get started? I have a really, really weird sense of humor, so just please bear with me because I think this is a brilliant one. You got to go get the code. If you're not familiar with Git, shame on you. No. Git is a software version control system. It's open source, written by Linus Torvald and a bunch of other stuff. Anyway, GitHub. It's on GitHub. You can go and find it. It's github.com/Rubik/Harbinger. There's not a lot on there. Where there's basically a shell script, the Python sensor code, and just a few other things that will be were either used in the old version or will be in the future version. So you can go and get the code. If you're in a Linux environment, Mac or something like that, you can just do a git clone from that URL, cd into the Harbinger directory, and you can just run the Harbinger script if that's one of your methodologies. The Harbinger script tries to go ahead and put the wireless card in monitor mode for you. I typically like to manually put my cards in monitor mode and stuff like that. But anyway, the first version of the code was approximately 209 lines of code. Thank you, Scapy. We're down to 99 lines of code of Python. I'm a horrible Python developer. I learned that if you just throw enough imports together, you'll get what you want. Somehow. But anyway, so it's very, very basic, very, very concise code, and I know you can't really see that, but I did try to make the code, once you get into it, as much readable as possible. Although I did perform the cardinal sin, there is 0 comments. So good luck. No, it's actually it is very, very intuitive in terms of what's happening in the code and stuff. You should be able to look at. Most people should be able to look at and go, got it. So what happens when we run the code, and you guys absolutely will not be able to, especially in the back, really determine what this is. And I think there's a laser here. Well, there was. Oh, you have to turn it on. Yeah. All right. So what we've got in this tall column here, this is, and we're going to run a live demo in a minute, and so we'll pray to the demo guys that all this works. But this is just basically some of the output of all the information that we're capturing. And I'll zoom in on the actual screen. And over here is looking at just the access points that we're capturing. We're looking at BSSIDs, the MAC address of the access points. We're looking at the SSIDs. Don't truly need those, but they come in handy for some other data analysis. The biggest thing that we're looking at is the RSSI, the signal strength, the transmission to and from the client and the access point. Because we're going to use this to do some really interesting math that I'm not going to actually get into because I don't fully understand it, but I know if I type in the values, I get the results I need. I had some really good help on that. And we're looking at all the timestamps of when the packets are captured and stuff like that. Very, very simple, very, very straightforward. So you go Raspberry Pi, laptop, doesn't matter. You download the code. What do you do now? Well, in of itself, a single sensor is not that powerful, although there are some things you can do it. The zombie talk that I gave last year, the first time I did it was in B-Sides Augusta. A gentleman named Tim Tomes, who's the author of Recon NG, was in the audience. And he got an idea based off of my talk, and he created a tool called WUDS, our Wireless User Detection System. And it's literally a proximity sensor at his house that detects anybody coming in with a certain radius of his home. It sends him a text message notification. So if somebody, UPS is pulling up in his driveway, he gets a text because he's actually detecting their cell phones coming into his. So it's like literally he's using a wireless alarm system. That's a really cool way of using like a single sensor. But for the most part, understand, we're trying to gather data, lots and lots of data. So we're going to design the grid, if you're any Tron fans out there. We're going to have an 80s party, I think, so we'll go Tron. The first question that I dealt with is, do I have to have 100% coverage? Do I need to cover every square inch of this, whatever area that I'm going, with all of these sensors and stuff? Because that can get very, very expensive, because that means I got to have a ton of sensors. And this is something that you got to keep in mind when you're actually designing. Anybody done like enterprise wireless deployments? Having to do tons of heat mapping and stuff to figure out where the ideal locations and stuff. You have to deal some of the same things. So questions to consider when you're deploying your sensors are, where are the choke points? Is everybody familiar with the concept of a choke point? It's basically a funnel. People have to enter and exit through the doorways. Back there, right over there, here. These are choke points. Okay? I don't have to cover the middle of the room. If I can cover the exits, you got to go through there sometime or die. Your choice. So it's about being strategic. Also, can a device in the grid be seen by multiple nodes? If one node can detect a device, that's great information. If two nodes can detect the same information, now we can start doing some really cool analytics. And also what happens if a node goes down. You do want to try to have some resiliency in your network. Do a little bit of overlap so that you can, because hardware fails. Pure and simple. So, depending on how expansive your coverage area will dictate how many nodes you require for your grid. This is just random. I think it's actually out of Huntsville, Alabama. Just picked it off of Google Maps and stuff. Let's say we wanted to cover this area. So, the first thing you have to do is you have to basically go into reconnaissance mode. You got to survey the landscape. You got to figure out what's around, what's going on. There's a lot of tools that you can use. I'm a big fan of Wiggle. I'm also a big fan of Kismet to map all the access points in your desired coverage area, because those access points are very important to our processing. You'll use this data to help fine-tune your node placements and things like that. And if you're not familiar with Wiggle.net, go check it out. Really, really cool. Your home wireless network's probably on there. So you've got to start determining your node placement. You're going to work there again. You determine the exact area you want to cover. Estimate where the choke points in your grid that require coverage. There will be some choke points that you can actually get away with not covering. Test a sensor at each point, looking for access points that are within range, not range, of the sensor. And you're going to cross-reference the Wiggle scans or Kismet scans to determine your sensor's effective range at current placement. I like coming, government people and stuff, like there's a bajillion acronyms. I like coming up with my own weird acronyms. I did it for the zombie talk, and I came up with one for here. And we've got what's called an ERD, an effective range of detection. ERD will vary from sensor to sensor through a lot of factors. Weather, topology, composition of, if you got sensors next to a steel building versus a glass building versus a grassy hill or something like that. you need to test the sensors at each location because the same radio stuff, you may only be detecting about 50% of the coverage that you did right down the street or something. So by calculating the ERD, if you look very closely here, you see this is from Wiggle. We see these access points all around this sensor here. Guess what? These access points aren't moving. They're stationary, which means for the most part, their RSSI is stationary. And this gives us points of reference to know that what our sensor is actually covering. So by putting our sensor in a single place, we turn it on, look for every access point around. We cross-reference those access points that show up in our sensor with something like Wiggle, and now we have easily determined what the effective range of detection on that sensor is. One of the nice things about a sensor network is because we're not dealing with transmission, we can have much longer radius of detection because we're not having to worry about maintaining a link or anything like that. So the noise level and stuff is not as big a deal. So you can actually get surprisingly good ERDs out of even low power radios and stuff. So what happens is you end up with this. Instead of putting tons and tons of sensors at every little nook and cranny, we're able to put fewer in strategic locations so that they overlap in certain places, especially at the choke points. And this helps save us money, but we're not losing any of the significance of the actual data. Now, if you can afford 100% coverage, do it. But most people can't. It's not realistically so. By figuring out where your ERDs and stuff are like that, you're going to be able to come up with ideal placements. You're also going to have to do this a couple of times. It's not going to just be very straightforward all the time because things change. ERD is very highly variable and constant calibration to maintain accurate data within the grid. This is one of the big caveats with sensor networks. So, moving on very quickly. Centralized data management. I've gone back and forth on how I wanted to do this, and I've basically made up my mind. I'm going to be using a system called ZeroMQ. It's basically a messaging queue that works really, really well and with Python. That basically each of the sensors are going to basically house a local copy of the data. Whenever a link is available, it'll queue the messages to the centralized server and then shut off. It's going to be really nice because it's going to, if we have active connection to all of our sensors, like they're on the internet, we will see all the data in basically real time. And because of real time, and because of the way we've done our coordinates and a lot of this calculation, I can actually watch a device move in real time through my network. Just like they're on camera. I just see a little waypoint because I'm able to use the RSSI, triangulation of access points and triangulation of sensors to do a bunch of trigonometry and all this other stuff that I don't fully understand. I just know the math works. And you're able to, real time, constantly calculate those waypoints through a grid. But it's not just for a single device. It's for every single device that's in that network. So, analytics and data visualization. Did I skip a slide? Nope. This is where the real crux of everything comes in. This is what's going to happen. The analytics and visualization is going to be written in R, and you're going to be able to select a bunch of your node cluster, and you're going to be able to zoom in, and this is going to be updating in near real time. You're going to be able to watch a bunch of data moving through your network. It's going to be really, really cool. This will be the last stage of the project. I'm shooting for November. One of the things is Harbinger. I'm a big fan of OpenWRT. It gives us a lot of people. The next actually big step, and this is kind of the step forward, is I'm actually building a custom OpenWRT image for Harbinger that will run on any OpenWRT compatible hardware. So you can actually install it on portable routers and stuff like that, which are tailor-made for sensors. So I'm having to take a little sidestep in the project, but it's going to actually become really handy because all you have to do, turn those things on, you're ready to go. This is coming soon. and by coming soon is eventually. Comments or questions? In the back, yeah. Yes. Absolutely. And there's another element too. There is a Bluetooth abstraction layer to this as well. It is not public yet because I'm still working out some of the kinks. From a data standpoint, wireless, roughly I get about 62% of all devices. If I do wireless and Bluetooth, it jumps up to over 94%. Because I can then start looking for LTE and stuff like that. Yes. The problem is that HackRFs and a lot of the software-defined network stuff is still not super cheap. So if you guys can bear with me just 1 second, I'm going to try to just give you a brief. If your devices are on, you're probably going to see them up here really quick. So this is just my laptop running, and it actually can't keep up, so it actually doesn't print every single one of them. And in the access points there, it's detecting access point, it's detecting clients. You're going to see, so most of our devices are actually going to broadcast and stuff. You can see the SSID, all the RSSI. So if I actually took my laptop around, you would actually see all of this changing. But if I had mapped strategically this room, you could actually then replay the path that my laptop took amongst you guys. And so this is just, like I said, that's all the data, and that's all the data that you can use. And this is all we need. A few GPS points when we deploy our sensors, and we've got a real-time surveillance system. I mean, traffic analysis system. A few. Oh yeah. You're absolutely correct. And just because it is a security conference, cat. Yeah, you're absolutely right. There again, I will not leave my objectives of making sure that we stay completely passive in terms of client interaction and stuff like that. It's just listening. But also it is you're limited what you can do with the cheap SDR dongles, and I can't justify deploying a $400 to $500 sensor when you do something like a HackRF, a really robust Bluetooth. I mean, you could easily spend $400 or $500. Now you're catching. You could, but you're still talking. I mean, but understand, a sensor like that, you're catching